Right, this is part 2 of the video to show how we can solve a system using MATLAB built-in functions. So this is one example. I talked about the two equations we want to solve, and this is a short script that actually links these two equations to the MATLAB solver. So these are, I think, the generic form of clearing the screen and clearing all or closing all the figures and clearing the screen, the command window. This is the command window. And so we're going to start with initial guess of 1 and 5. We set the options to display an iteration. We want to show basically every iteration. That's what we set this up. Okay, and then we call fsolve at the function name, initial guess, and option. So this fx is given down here. And this is it. I think there's nothing more than that. And I'm only interested in the solution. So I put the outcome of the fsolve, or the output of fsolve, to be the solution, comma, tilde. So this tilde means whatever that is, we don't care. And we are not interested in anything other than this. So we put comma, and then a tilde means whatever the rest of the output is supposed to be. I'm not interested in that, and I'm not going to get it. Okay? All we get is the solution. Okay. So let me run the code. And there you go. So here's the output. Number of iteration. Function counts means how many functions were evaluated basically at this iteration, which is not so much of interesting point to us for now. And this is the f of x, which is supposed to go to 0, and you see that it gets to 10 minus 22, which is almost 0. And this is the norm of step. That means norm of delta x at every step. And yeah, these two are other things. They actually talk about it maybe in the next 2 weeks or so. All right, and here's down here is the solution, 1 and 4. And if you plug in these two into the equations we had here, we should see that both actually satisfy the two equations. So that is it. This is the first example. By the way, this code is also on Blackboard. So if you go to the script tab, you should see the function called, or the script called nonlinearsystems.m, which means MATLAB script. All right, fine. Let me comment out these lines and talk about the second example. So here's the second example. I'm going to uncomment them. Okay. And then this time I'm going to use a different function. So now we're going to use solve. I hope this is clear by now that solve solves the system symbolically, but fsolve that we saw here solve stuff numerically. All right. Okay, so we're going to clear the screen, clear all the variables, close all the figures, x and y are symbols, and I have two equations to solve. X squared plus y squared, x squared plus 2 times the square root of y is equal to 1. And you see that this time you have to write equality with two equal signs for the solve function, because everything is symbolic. And the second equation is the third root of x plus y squared is equal to 2. I'm interested only on real roots, not imaginary ones. And I believe this is to check the condition number to see if the condition number is big or not. And this is it. There's nothing more than that. On the output side, I'd like to see the solution for x, for y, and the convergence flag means that whether the code converged by the time I get the solutions or diverged. And this parameter, can't remember exactly what it was, but let's run the code and see what we get. Alright, so I'm going to expand this window a little bit. Here you go. So the solution to x is u to the third power. Solution to the y is u to the 12th divided by 4 minus u to the 6th divided by 2 plus 1, 4. Now one thing to note is we didn't have u there. And suddenly u shows up. If you look at the here, I only have x and y. And all of my equations are based on x and y. But suddenly in the root, the solution, I get this weird variable u. and everything is based on u. The x is based on u, the y is based on u. So the question is what basically u is. Okay, so u is something that we can define later on. I mean, that's an option. Looks like the system has many roots. For every u we put in there, we get a solution for x and y. Okay, we know that nonlinear systems can have multiple roots. It's not like we have two equations, two unknowns, we always get two solutions. Okay, that is only the case for linear system. For nonlinear ones, we can have multiple roots, and that's what this is. It says, well, x is a function of u, y is also a function of u. For every u we select, we're going to have a set of 1 x and y. Okay, now what is u? Well, it has actually a constraint on u. It says, okay, u cannot be anything as long as u satisfies this weird equation. Okay, then once you plug in u into here and there, you get the x and y. So that's what actually the symbolic solver does. It really doesn't show like completely independent solutions. Looks like the solution is a function of u, and there's another equation for u. But anyways, I think that's better than nothing. At least we get a solution symbolically. Okay, hope this is clear that we have to solve this equation. This is one-dimensional problem. We have to solve this by ourselves to get u. Once we get u, we plug in u into the x solution, y solution. We get the pair of x and y, which is the solution of the system. All right. I hope this is clear, and that's the last example we had for solving system. Okay, so thank you so much for watching. Stay tuned for the next video on linear programming and optimization, which is going to be the next chapter in our syllabus. All right, so thank you so much.